In this video, we're going to go through the beginning of chapter 4 in the statics textbook. So chapter 4 is on force system resultants. The chapter starts by introducing you to the moment of a force and talking about the precise definition of a moment. In the previous two videos, we go into this in detail. So I'm not going to spend too much time on some of these sections. We're just going to skim through it, and I'm going to clarify certain points that I think may have been confusing to you in the previous videos. But once we get through the first few sections, we're also going to talk about the idea of the moment of a couple. So at the end of this video, we'll talk about the moment of a couple. Okay, so as I mentioned in the previous two videos, we talked about the idea of what is a moment and what is the precise definition of a moment. Like how do you calculate a moment? And so a moment of a force or torque, that means the same thing, is the tendency of a force to cause rotation. That's the general definition. Now, more specifically, the tendency of a force to cause rotation about a point. But you can also say, what is the moment of a force about an axis, if you want? Like specify an axis and find the moment of a force about an axis instead of a point. You can do that. And in general, the moment of a force about a point or an axis is the magnitude of the force times the perpendicular distance from the force to the point or the axis. So that distance is perpendicular to the line of action of the force as well as to the axis or to the point. You can't really be perpendicular to a point, but we'll talk about that in a second. That perpendicular distance is called the moment arm. So the force times the moment arm relative to a point or an axis, that is the moment of the force about that point or axis. That is a measure of the tendency of that force to cause rotation about that point or axis. Okay, and so here's that general definition. It's F times D. And they give an example here. So you've got the force, and here's this distance. It's perpendicular to the force line of action and to the point. Or you can think about it instead of the point, the axis of rotation. And the axis of rotation is perpendicular to the plane that contains the moment arm and the force. You get that using the cross product, right? The cross product gives you a vector. The direction of the vector is perpendicular to the plane of the two vectors you're crossing. Okay, so it talks about just the general definition of the cross product here, which we talk about the cross product in the vectors in space video. And there's also another video where we work an example of how to calculate the cross product. But okay, so R cross F, the moment of a force about a point is R cross F. And so if we look here, you can't be perpendicular to a point, right? How is a line perpendicular to a point? But when you calculate the moment about a point, you get this resulting moment axis, which comes from R cross F. And again, I don't want to get bogged down in these sections. I went into full detail about this in the previous couple of videos. But one thing I want to clarify is, so we mentioned that the moment vector is a fixed vector. Its tail is fixed at the point of interest. And one of the reasons you can think about it, of why that is because, like, if I calculated the moment of this force about this point on that same axis, I'm going to get a different vector. I'm not going to continue to get the same vector, right? Like, think about it. Like this, if I do R cross F here at this point, well, this is a different plane now. I've got R and F are in a different plane. I'm going to get a vector that's in a different direction. And so now, okay, now you might say, well, this is still a sliding vector because I can slide this moment vector, and the moment vector is not changing. And really, no matter where I apply this moment vector along this line of this axis, it's the same rotation effect on the body. That's true. But when you think about whether something is a sliding or a fixed vector or a free vector, you have to look at the full picture, the full context. If I change the position of this vector, then I'm changing the force. Like I'm changing I have to change the position of this force relative to the point. I'm changing the loading on the body. I'm changing the problem, right? Because again, like if I can calculate the moment of this force about any of the points, any of these points on the body, it's going to be a different moment every time. I mean, there might be a coincidence to where some are the same, but like in general, it's going to be different. So I can't just move the moment without changing the whole problem. If I could move this moment and it wouldn't change the problem, like for example, when we calculate, we talked about in the previous videos, and we're going to talk about that later in this video, how when you're calculating the moment of a force about an axis, okay, you're not calculating the moment of a force about a point. If you're calculating the moment of a force about and some axis you pick, the moment of this force about the x-axis, or the moment of this force about the z-axis, or the moment of this force about this axis, then it's a sliding vector because think about the context. That moment, the moment of the force about a specific axis is the same no matter what point I choose on that axis to calculate the moment. Like it's the same. You can slide that moment without changing the problem. And no matter where that moment is, you're still just, what are you creating? Like a moment about this axis. You're just talking about a spin or a tendency to spin about this axis. And that's the same no matter where the moment vector is. Okay, and so if we come here, this principle of transmissibility, that's kind of what we're talking about. The cross product operation is often used in 3 dimensions since the perpendicular distance or moment arm from point O to the line of action of the force is not needed. In other words, we can use any position vector R measured from point O to any point on the line of action of the force F, right? Like they talk about here, R1 cross F, R2 cross F, R3 cross F, you get the same moment. So this force is a sliding vector in that context, right? That's what it says here. Since F can be applied at any point along its line of action and still create the same moment about point O, then F can be considered a sliding vector. This property is called the principle of transmissibility of a force. Because no matter where you put the force along its line of action, you get the exact same result in the context of calculating the moment of this force about point O. In a lot of situations in statics and mechanics, we're going to find that forces are transmissible, not just for forces acting as moments, but forces in general. Like you can apply in the statics problem, you can apply the force to the body anywhere along its line of action, and you're going to get the same result of the final result of the problem is going to be the same. Now that might be confusing. You might be saying, well, no, if I pull on something versus push on something, that's intuitively that's different, right? So like if you had a block, right, and they're saying that, so you've got this force here, but I could also apply that same force here, and it's the same result. Well, no, if I push on it versus pulling on it, it's different. We're talking about from the static analysis standpoint, right? Just from the standpoint of analyzing it's like from a mathematical standpoint, from a mathematical vector standpoint, you're going to get the same result no matter where you apply the force along its line of action, right? So here you get the same result no matter where you apply this force. You get the same moment about point O, no matter where you put this force. It's not like if all of a sudden I move the force, this moment's changing. Or if I take this moment and I slide it up and down, right? The force is a sliding vector, but the moment is not a sliding vector. If I slide the moment up and down, yes, if I do slide the moment up and down and I literally don't change the moment, well, in that case, yeah, it's a sliding vector, but for the context of this problem, if I slide the moment vector up and down away from the point, then I have to change this then the moment's going to change. Because now I don't have R1, R2, R3 cross F anymore. I've got a different scenario. So I hope that makes sense. Okay, so then here we talked about how this is the determinant form of the moment of R cross F, and they expand it out. So like here's the position vector Rx, Ry, Rz, and here's the force vector Fx, Fy, Fz. And you can see what the components of the moment vector are, like the components of this vector. The I hat is the moment about the x-axis. The j hat is the moment about the y-axis, the moment of the force. And you can see it in the context of the components. So like here's the moment about the z-axis. Rx, Fy. Okay, so here's Fy and here's Rx, right? So that's causing a rotation about the z-axis. If you use the right-hand rule with the curl, with the thumb in the direction of positive z, that's a positive rotation. So this is positive. Minus Ry, Fx. Yeah, so Fx, Ry. And then Fz is, and then that's negative, right? That's causing a clockwise rotation if you're looking down the z-axis. And then, so it's negative. And then Fz causes no rotation about the z-axis. So, okay, we talked about a lot of this in the previous two videos. All right, the principle of moments. A concept often used in mechanics is the principle of moments, which is sometimes referred to as Varignon's theorem, since it was originally developed by French mathematician Varignon in the 1600s and 1700s. It states that the moment of a force about a point is equal to the sum of the moments of the components of the force about that point. Yeah, so we use this in, we just saw this when we were looking at the, we broke the force down into components and looked at the moment about each axis. But we do this in 2D. This is like the way we work the problem in 2D. You take the force and you break it up into its components, and then you sum the moments of the components about the point, right? Fy times x, that's positive, and then minus Fx times y, and that gives you the moment of the force. But you can see though, like this is a 2D problem. You do it by components, but if you're looking more for the intuitive definition of the moment, forget the components, you extend the line of action of the force, and then you get that perpendicular distance to point O, to the point, multiply F times D, and that's the moment. We don't really do that when we're doing 2D problems, but that's what R cross F is doing. Now, you could do this. You could do it this way in 2D, and it wouldn't be that complicated. But this is harder to do in 3D. But why is it easier to do in 2D? Because the moment arm and the F in 2D are all in that 2D plane. So in and out of the plane, you're guaranteed to be perpendicular to the O axis, or not to the O axis, to the Z axis, because it's coming in and out of the plane. Any line that you draw in within that 2D plane, if you draw it to O, that's perpendicular to the axis that's in and out of the page at O. So all you got to do is make sure this is perpendicular, and you got it. In 3D, it's harder to, you're not looking straight down at your plane. So it's harder to see, am I perpendicular to the resulting, or to the plane containing R and F? Like, you have to make sure, that's what the cross product helps you to do. But you could do the cross product in 2D. You could find the force. You could get this force as a vector. It's going to have just two components. Get a position vector to anywhere along this line of action. It's going to have an I and a j component, and cross those. Okay, so we're going to work a bunch of problems. Okay, so the moment of a force about a specified axis. Instead of a point, you might want the moment of a force about a certain axis, right? So they show this here. You can say, what's the moment of this force about point O? Okay, but that's going to give you this moment vector here. But you really want, all you care about is the moment, what's the moment, the resulting moment of this force about this axis. And so if you can do this with vectors, and we'll talk about that in a second, but if you want to do this manually, the whole idea is you need to find the distance that's perpendicular to the line of action of the force and perpendicular to the axis that you're interested in. So it's perpendicular here, and then this is perpendicular here, right? Like, you can extend this. This is D, perpendicular here and there, right? So you wouldn't do, if you extend this line of action, you wouldn't do this, right? So if you do force times that perpendicular distance, that's the moment of the force about that axis. Now, when you're doing this, note that if the force line of action is parallel to the axis you're interested in, then the moment is 0 about that axis. If the line of action of the force and the moment axis and the axis you're interested in intersect each other, then the moment is 0. Okay, now doing this with vectors, what you do is you find r cross f for any point along that axis that you're interested in. Now, depending on the point you select, you're going to get a different moment vector, but then what you do is you project that vector, you find the projection of that vector onto your axis. So when you do r cross f for any point along that axis, the vector you get is going to be on that axis, like something like this, right? Now, when you dot it with the unit vector for that axis you're interested in, then you get that component along that axis. You get the magnitude of that component. If you want it as a vector, then you multiply it again times the unit vector. So we talk about projecting vectors finding projections of vectors onto certain directions in the vectors in space video. But you can see, though, in this case, you have a sliding vector. When you're finding the projection or you're finding the moment of a force about an axis, that's a sliding vector. Now, that's confusing, right? How can that be a sliding vector? Think about the context, okay? We said no matter what, you can pick any point to start with as your starting point along the axis, and you're going to get the same result. So if you slide that moment vector on that axis anywhere, you're not changing the force, right? To slide that vector, you don't have to change the whole force system. If you found the moment of this force about this point, and here's the result, this, right? Well, now you can't just go sliding this vector without changing the whole force system, right? I know it's really confusing. It depends on the question you're asking. So, like, okay, if you found r cross o and you got this vector here, that's r cross or r cross f with the moment of f about o. Now, if you're just asking, okay, what about the moment of this vector about this axis? That's the context. Well, then you can treat this as a sliding vector because you can calculate the moment of the force about any point along this axis, and then once you project it onto the axis, you're going to get the same vector, right? I know it's confusing. Just try and pause the video and think about it. Like, if you're talking about the moment about a point, it's different, though, because you're going to have a different moment no matter where you calculate, depending on which point you use. So, but here, just talking about the moment along this axis here, it doesn't matter where you apply that moment, you're going to get the same rotation of the lug nut. The whole idea of transmissibility of a force, sliding vector, free vector, is that whenever if you can move in the context of the problem, you can slide that vector on the line of action or move that vector in 3D space, and you're not changing the problem, the statics problem. That's the idea. Okay, the moment of a couple. A couple is defined as two parallel forces that have the same magnitude but opposite directions and are separated by a perpendicular distance d. Okay, so here's a couple. Two forces, they're parallel, they have the same magnitude but opposite directions, and they're separated by distance d. That's a couple. So the resultant force is 0. The only effect of a couple is to produce an actual rotation. Or if no movement is possible, there is a tendency of rotation in a specified direction. Right. Okay. For example, imagine that you are driving a car with both hands on the steering wheel and you are making a turn. One hand will push up on the wheel while the other hand pulls down, which causes the steering wheel to rotate. Right. So if you look here, that's a couple moment, right? Parallel forces, one in one direction, one in the opposite direction, separated by a distance. Here's another couple, but the distance between them is less, but the forces are higher. So I'm assuming this must be an equivalent couple. Yeah, because we're talking about equivalent couples. Well, okay, we'll get to this in a second. The moment produced by a couple is called a couple moment. We can determine its value by finding the sum of the moments of both couple forces about any arbitrary point. So here we find the moment of this F about point O and the moment of this minus F about that same point O. So the couple moment is determined about point O is, so RB cross F plus RA cross minus F results in RB minus RA cross F, but RB minus RA is just R, so this M is R cross F. Okay, so what does this mean? This result indicates that a couple moment is a free vector, i.e. it can act at any point since M depends only upon the position vector R directed between the forces and not the position vectors RA and RB, directed from the arbitrary point O to the forces. This concept is unlike the moment of a force, which requires a definite point or axis about which moments are determined. Right? So the moment of a force about a point is a fixed vector. The moment of a point of a force about an axis is a sliding vector. And then a couple moment is a free vector. And it's going to be important to understand sliding vectors and free vectors and fixed vectors later in this chapter, if we want to rearrange force systems and mold force systems in different ways. And force vectors, so the vast majority, if not all, I'll find out exactly, force vectors on bodies are sliding vectors, not just in the context of calculating moments of vectors, sliding vectors in general. For all circumstances, you can force vector, you can slide it and it won't change the result of any statics problem. Okay, the scalar formulation for the moment of a couple, you say that the magnitude of the force, so F and minus F, take the magnitude of the force and multiply times the distance, the perpendicular distance, or the moment arm between the forces. So like this is perpendicular. Now, if you want to do it, if it's more complicated and you want to do it as a vector formulation, you do R cross F. R in this situation, like we talked about, is if we come here, it's this. This is R. It's a vector that's between the forces. And it doesn't have, the R doesn't have to be perpendicular to the forces, just any vector that connects the lines of action of the forces. Okay, so in the scalar formulation, the axis, the moment axis, is perpendicular to the plane of the two forces. And you use the right hand rule. You put the curl of the fingers of your right hand in the direction of the rotation, and the thumb points in the direction of the moment axis. So the magnitude of the moment is that F times D, and the direction is using the right hand rule. R cross F, same exact idea as the scalar formulation. Okay. If two couples produce a moment with the same magnitude and direction, it has to have the exact same direction. So remember, if we come back here, remember, a couple can be in any orientation. So a couple moment vector can be in any orientation in 3D space, right? Okay, so with that in mind, if two couples produce a moment with the same magnitude and direction, those two are considered equivalent. And they give this example here. So these two are equivalent because whenever you reduce the moment arm, you increase the forces. Okay? Since couple moments are vectors, their resultant can be determined by vector addition. For example, consider the couple moments M1 and M2 acting on the pipe in figure 429A. Since each couple moment is a free vector, we can join their tails at any arbitrary point and find the resultant couple moment. Cool, right? So you're looking at what's the effect of these couple moments on this entire like body here. This like a full rigid body here. Well, these are couple moments. So and now be careful. Make sure you know the difference if it's a couple moment or what type of moment it is, or a moment about a point. I'm not sure how they don't show how you distinguish between a couple moment and a regular moment. But if you've got couple moments, you can just sum the vectors. They're free vectors. You just bring them together at any point you want. You can put it at any point you want. Interesting. And you just do the vector sum. And so like they do the vector sum here, and there's the resultant couple moment vector. Now, what you can think about is, what if you had a moment about a point, right? A moment about point O. So that's a fixed vector. But if you had also had somewhere else a couple moment, you could bring that couple moment to that point O and do a vector sum. And so that's what we're gonna talk about later in this chapter, how you can simplify force systems and moment systems that way. Okay, so we're gonna work a bunch of problems so you can get a good feel for this. Okay, and then next we're going to talk about the simplification of force and couple systems, right? So you can rearrange forces, move forces around, like we said, like move a couple to a point and sum that with a moment about a point. Or maybe you can move a force, but you have to add if you want to move a force, you can move it, but you have to add a certain moment to correspond to that movement. So this is very interesting stuff.